Welcome everybody. I'm glad you all, could squeeze some time into the busy afternoon to spend with us. And we've developed something we think is probably the best thing out there, and we wanted to take a moment and share it with you. And so right now we're going to talk about the Siemens Engineering Design Curriculum, which is a STEM-based curriculum that we, think will prepare young students for the next, at least their workforce for the foreseeable future. And so my name is Tom White. I'm basically an educational consultant, and I work with a couple other folks. Dick, why don't you introduce yourself?
Okay, Tom, my name is Dick Blaze, and I have been associated with Tom White for probably 35 years now. We worked at the same school together where the engineering curriculum that became Project Lead the Way was created, and then of course the two of us launched Project Lead the Way. We then went on to work at the Southern Regional Education Board together, and now we are working developing these courses for Siemens, and it's a pleasure doing this. I will say it's, in my opinion, it's the best work that we've ever done. So hopefully you can agree with that, I hope, by the end of this presentation. Tom?
And so the only handsome guy up there is Matt Bruce, who he works for Siemens, and he's basically in charge of the America's Solid Edge academic program. And so I contacted him several years ago and told him about the work I was doing with the Southern Regional Education Board and asked if they could help us out. And so he made software available and that type of thing. And I got to the point where I needed something a little bit more, and it hadn't been developed yet. So he asked me if I was interested, and Dick and I said, well, sure. There are a lot of steps in between there, but we wanted to make sure that, we credited Matt because he was the brains behind the whole thing. So when we started thinking about creating a piece of curriculum that schools could use, we wanted to figure out, well, what were the things that people said they needed from the next generation of the workforce. And so there's an association of colleges and employers. It's called NACE. And these are their top 10 skills. So it started with leadership and abilities to work in teams and communication of all types, problem-solving skills, work ethic, initiative, quantitative skills. And you take a look at all those, and those have nothing to do with, really straight technical curriculum. So we wanted to make sure that we included enough things in this curriculum that we would touch on all these things and give students some practice. Because if they can speak intelligently and they can write so people can pay attention, and lead teams and problem solve, they'll be fit for almost anything. And then, in our conversations with colleges and, other employers, they said that they really needed students to have more experience with Excel. I guess it's an analytical tool that most businesses utilize. So to accomplish this, we wanted to make sure that the curriculum was project or problem based. So the way we did this was to divide what we thought were the learning objectives for the entire course, created our own set of standards for them, and then put them in a logical order, and then wrote projects to fit that. And Dick will talk about that in a second, because we thought that that was the best way to get students ready. And then you'll notice that, there's, the pencil is the tool being used here. There's some precision measurement going on. And that's what we really want to have happen is to create a forum so students can record all their information and think about what they're doing before they ever touch a CAD system. You know, the CAD system is a tool it's a really great tool for documentation, but the thought process needs to be built in beforehand. And so our bottom line on this was the software should be available to schools at no charge. And you know, the curriculum and the software is a nice combination, which really kind of moves things forward a little bit. And, you know, what you're looking at is a team of students that are like working through a problem. They have to problem solve. They have to talk about what they're doing, why they're doing it, and how they're going to approach it. So, Dick, you want to talk about the, you know, familiar context here?
Okay. You probably have heard this phrase, rigor and relevance, and it applies to this program. When Tom is going to go through the curriculum, one of the things that you'll see is all the projects are in a context that students can relate with. There are no unfamiliar things. They're all familiar, but the challenges are still rigorous. In addition to the rigorous challenges in the projects, you will also see a number of standards from the academic core, reading, writing, listening, and speaking, as well as mathematics and the next generation science standards, and also the technical standards that we have written specifically for these projects. So when you're working with colleagues in your building that are teaching math or science or English or whatnot, you will be able to share with them the kinds of selected, specific, most important standards in their discipline of math and English and science that relate directly to the project. And so it makes for a great tool for teaching integrated learning, and it makes for a great tool for collaboration across disciplines. And if you're in a traditional configured school, that can work. And if you're configured in an academy model, the tool is very supportive of that design. So let's move on, Tom. Thank you.
All right. And so we you know, as Dick said, we integrated standards from several different areas that we think are important to those you know, those skill sets that the you know, colleges and employers said that they wanted. So we, you know, on each project we specifically outlined a few, and you know, I'll get around to showing you some in a couple of seconds. But you know, that way you can talk with your curriculum people, and you know, even when you go to do board presentations, you could say, okay, this not only, you know, gives the kids something that they need to help them with their employability in the future, but it also meets the goals and, you know, stated objectives of the school. The students will do better on their math and literacy exams. And you know, I don't know about your state, but my state has a report card for every school about how well they're doing on these things. And anything we can do to make them look better is a feather in our cap. And we talked about that the students are always in teams. You know, when we first start, we have very small teams. We like to have people be busy. It keeps them out of trouble. We also want to make sure that everybody has a chance to be a leader and to take on different roles in the teams and to be able to run through the whole design process, because that design process is what really brings home the education for students. In this first course, there's extensive use of 3D printing. It's one thing to draw a nice CAD picture, but it's something else again when you actually got to create a part from it. And you know, students find out that, okay, you know, if three of us are working on different parts that all have to fit together, we have to speak the same language. We have to discuss in advance what our tolerances are going to be, because if I make a 1/2-inch hole and you make a 1/2-inch shaft, unless we have a way to do an interference fit, there's no way that we're going to get those two things together. So those conversations become important. And those conversations lead to the speaking and listening part of the literacy standards. We go through and students take common everyday things. Dick talked about something they recognize. So there was a team of people that decided that they wanted to reverse engineer a clothespin. And so the first step in reverse engineering a clothespin was to do accurate drawings of various parts and how they fit together. And so they did that. And then they printed it. So the piece on the bottom is actually the printed clothespin. So they had to print the various parts and then get them to go together. And they had the most problem printing the spring. If you've done any 3D printing, you know that a spring is really kind of difficult because of the way it's shaped and how we want it to behave. But they mastered it. They learned a lot in the process. So we use a design process with the students. And the first step in the whole thing is they have to do some research. They have to do some background. It's like, okay, here's your problem. And so to keep them from solving the wrong problem, the first thing they have to do is figure out what the vocabulary is talking about and, what are some things that are, important to know before we get started. And then we have to do something I call propose. It basically is a way to come to an agreement with the people that provide you with the project. For example, if somebody asks you to solve a problem, you're going to say, okay, this is how I envision the problem, and these are the things I'm going to do to solve it. And you come to an agreement before you ever go any farther, because if you don't, then you do an awful lot of work and nobody decides to pay you for the work that you did that nobody agreed to. So once we finish the proposal and everybody's agreed, then we do a little bit more research so we understand everything that we didn't know before. And we get around to actually building a physical design, which is all part of the documentation process. So we want to not only create physical designs, but we also want to go in and do a management plan for the project. We also want to make sure that we do some analysis of our design before we build it. And we want to design a testing protocol before we get there. But we'll talk more about that later. You build it, you test it, you analyze it and evaluate. And then there's my favorite word, iterate. I've had many people ask me, well, what does that mean? If you're from the engineering or technology world, you realize it's just a simple way of saying, okay, we go through the whole process again. We finalize the design and we communicate about that with everybody. And, if we follow this, there's several opportunities for literacy in here, because we're always writing something. We're keeping notebooks, we're sketching, we're creating all kinds of documentation to be analyzed. So we're also doing mathematical analysis. So that means that we're hitting on math standards. And it really works out pretty well for everybody. And I want to take, drill down, do a closer look. This young woman was actually on Good Morning America. She used this solid edge design software to design a prosthetic foot for a soldier that was injured in Afghanistan. So this is one of those, opportunities to, give a student group a real problem to solve, and they can go ahead and work on that, and they really connect better with what they're working on if there's a challenge to it and they accept that challenge personally. So the next thing I want to take a look at, I think I want to take a look at it. There we go. So the curriculum is designed to take 4 quarters. Depending on your school setup, you can do this in any number of different ways. I know it's done in career centers, and they'll do it in a half a year. I was working with a school district in one of the southern cities that decided that this first course really impressed them, but they didn't think their students could handle it right away. So they're doing it over 2 years. And, maybe once they get the ball rolling and they figure everything out, they can reduce the time they're spending on it. But, it gives them a lot of flexibility. So the first quarter, we first talk about the design process, and then we go into sketching and documentation. So we learn how to use those pencils to come up with things. And then we introduce a CAD program by the creation of a solid model and printing it out, just to show them that they can do it. The goal here is not to learn a design tool. We're not teaching commands to click on, that type of thing. We are trying to teach the thought process behind it, and then students will figure out the software, how to learn about the software, and they will be keeping up with it as iterations come along in the software. Once you get through that, then the rest of the first quarter, there's a simple project that kind of cements the knowledge about creating things three-dimensionally. So you have a choice here, and the teacher can either pick one for everybody, or you can allow different student groups to work on different things. So there's a sport drink container, which contains a mathematics for figuring out volume, and so when you go to design a container for it, that you get the right size. There's a design of a kitchen tool. Some things that really upset kids is, why should I have to do this? I should be able to do that. Or a chess set. Then later on, they get into renderings, working drawings, and design presentations. So shower caddy rendering is, basically allows them to practice photorealistic type applications from their CAD work. Then we get into an Excel project, which is a table-driven kitchen measuring. So we can put all these dimensions on a CAD drawing, and with a few simple clicks, change what we're doing. So if you wanted to go from a half a cup to a cup measurement, for example, and maintain a similar shape, because if you think about a Coke bottle, for example, it has a very identifiable shape. So if you want to continue with that, then all you have to do is change a few dimensions, and the whole thing changes your output. The second quarter, we basically are working with assemblies. How do you take multiple parts, put them together, make sure that they all work, and take things from there. So the first project is a three-dimensional puzzle. So the kids decide what kind of puzzle they want to build. Then we take them through a mold design where they can actually go through and create a cavity and then do some casting. It's very common to use a microwave and chocolate or something just to bribe the kids, but there's a lot of different materials that you can use, that you can put in there and come away with a solid. There's something we call a coach's cart. Most schools have athletic coaches that really their office in one place, and then they have to take all kinds of things out on the field. And so what the purpose of this one is to convince students that they have to interview clients in order to build something that fits the client's needs. So if they can poll a coach and say, okay, this is what we want to put together for you, and then the coach can say, have input, and it's really kind of a nice two-way street. Helps the design process. And the last project is designed to introduce students to different engineering features. So they have to pick something, take it apart, build a three-dimensional view of it, do all the drawings for those pieces, and they could even go in and redesign some of the parts, print them out and put it all together. And it really shows the nature of assemblies. part of manufacturing is not only design, but design for manufacture and design for assembly. How quickly can we put something together? The third quarter, we begin with simple machines, and the project choices here is either a nutcracker or a bathroom door latch, something that will say occupied, when you go in and throw the latch. It gets them used to how things work together, how energy is transferred from place to place, and all kinds of things related to simple machines. Then there's one called a ball launcher, which is, again, another Excel type project where students have to design something and print it out that will launch a ping pong ball and then figure out how to predict the path of the ping pong ball so it always lands where they want it. So one teacher, puts a bucket in the middle of the room on any given day and says, okay, you got 2 test shots and then you have to land 3 balls in the bucket. So it leads to an intensive discussion about how Excel can be used to create mathematics that'll allow you to do that. Then we talk about mechanical systems. So there's some gears involved that they do. Solid Edge has a nice gear design tool, so they'll be able to create gear systems and various ways of transferring force from place to place. It's a nice tie-in with science. In addition to the, in the next generation of science, there's the engineering design standards, but there's also standards on transfer of force and all kinds of other things that this helps the projects meet. And then a mechanical system, and this one was a merry-go-round. And, as a grandfather, I get to playgrounds quite a lot, or at least I used to. Some of the kids are a little old for playgrounds now, but the ability of a small person to exert some force and cause movement is a wonderful thing. So,
and Tom, in this project, the students learn about
the fourth quarter. We talk about structures and forces. And so the very first one, they're designing a pedestrian bridge. So they have to figure out, what's the span, how much force is going to go on it, how do we analyze those things. So they learn some of the finite element analysis tools that are included with the software so we can predict how much something is going to deflect. We then go to a hybrid toy connector. So, all those things that we step on in the middle of the night and, bruise our feet with, it's like, how do we take one, so like if we wanted to connect a Lego up with something from Fisher Technics, can we design something to go between the two of them? Kids get really used to designing the things that they need, as soon as they have the tools in place, where they know how to work a CAD system and then they know how to work a 3D printer, it's always good. And the last couple here, there's a playground design where they get to design an entire playground so different student groups can combine their designs together and come up with a design for a total playground. And the last section of this course is talking about engineering systems. So they have to pick one of these 5 and then go ahead and solve that. So I want to show you briefly. Here's the first project involving a CAD system. Just an easy way to show you how they're all fit together because they all follow a similar pattern. The first piece is an introduction, which tells us what it is and why we're doing it. That's under the purpose is the why. So they become, they understand what they're doing and why they're doing it. We have a whole series of concepts that we want the students to understand at the end. There's an outline of the entire program at the beginning, but this talks about the sections of the outline that it covers. We get into the standards, and the standards are basically things that we identified as important things for the course to cover. We wrote measurable standards for it, and you'll notice they're all, if you look at Webb's, development, these are all, third and fourth level to, say, okay, we're analyzing, we're building, we're creating, et cetera, et cetera. Math standards are listed here. For example, in this one, we're dealing strictly with geometry. So the modeling with geometry, and it goes and tells us which ones of those that we're actually using on the project. Then we've got reading, writing, listening, and speaking. We go into the next generation science standards. So here are the practices for design and modeling. Standards for the technological literacy. So for states that need these to qualify for Perkins funds, these are here for your use. We talk about how do we assess these things. So when you're doing writing or creating projects, then we're really talking about rubrics. So in this case, if we go, here's a rubric, and it's basically set up for like, well, what are you creating? How are you communicating about it, and that type of thing. And so then after the rubrics, we basically start with an essential question, because project-based education always poses a question for students. Then we give them a scenario, and the scenario allows them to explore careers. So who does this kind of work? And if it's exciting, then what kind of education would I need? Where would I work? How much would I be paid? That's kind of an important one for kids, especially if they think $10 an hour is a pretty good wage. And then we start talking about, well, what do you really need? We talk about what are the deliverables that they have to create. And then we give a daily plan. And so the daily plan is based on the design process. So we say, okay, here's the design process. And so this is all linked together. So, we talk about conducting preliminary research and go ahead and making a design brief and budgets and schedules and all kinds of things. So like to create a design brief, we'll give you an example of what a design brief that a student would do. So there's the client and the context of the problem. There's the problem statement, criteria and constraints, etc. So, and you'll notice it all fits on one page. And I tell students that, a design brief is like an elevator speech. Basically, if we can agree on everything, then we're good to go. We can do a detailed proposal from that. So that's an important thing. Hopefully I'm going to the right page. Okay, and then, so the testing protocol, management plan, these are all outlined here for you. And then students, research the vocabulary terms. So that's that preliminary research we talked about a little bit before. We allow student teams to meet and discuss and work. So you're going to see there's an awful lot on the teams in here. All right, for those of you who have to make lesson plans that say this is what the teacher will do and this is what the students are doing. If they take the whole document, great. If not, you can just cut and paste in a fairly rapid and spend all your time working with students. Then there's some links to some preliminary things. We call these enabling activities. In order to understand what a CAD system is, you're going to have to go create some sketches and be able to define the sketches and understand what all these things mean. And some other exercises, and then we cut them loose. We say, here's how the help system works. And if you have questions and your team can't figure it out, then come see me. And at the end, there's a list of 2D or a list of vocabulary, and then some resources. So where do I find examples online? What are some good videos to start with, some tutorials, things on engineering reports. Now, as the projects get more difficult and later on, you'll see this list of resources take up several pages. So I've talked a lot about how this works and what the projects look like. Are there any questions? Okay, so I've just put up the slide that'll tell you where to go and download the curriculum from and get more information. And Dick, if you could read the questions, maybe we could tag team the answers and see if we can, move things forward.
Okay, well, the first question I have is, Brad was asking if there are grants through Siemens available for the 3D printers and computers to design the projects.
Okay, I suppose either one of us could do this. Siemens doesn't have a grant program right at this point, but I know we work with some schools in Michigan who work with a manufacturing association, and the manufacturing association, set the school up to get it going. So we can give you a hand identifying those businesses in your communities and maybe help you out on that.
And also, everybody needs to understand that the federal government provides money through the Carl Perkins Act that is given to each state on a per pupil allocation, meaning that big states get more money than the little states and so forth. But that money is intended to help schools implement programs like this. And depending upon what the state plan calls for, you could have access to those funds, but you need to check with your state director of career and technical education at the State Department to determine that. We have another question. Brad teaches in a Title I school, even though they have a 1-to-1 ratio of iPads to students, their computers are not basically powerful enough to run a CAD program or operate other high technologies like that. How can they be effective in this situation? What can they do, and what are the computing requirements for a curriculum like this, Tom?
Well, it depends on the version of the Apple product that you have. Most of those you can use a product called Boot Camp, which is available through Apple, and that'll partition a hard drive so you could actually put a version of Windows and run the software on it. The problem with many of the schools is they got a like a bare minimum setup for those computers, and there's not enough space. So the short answer is, yeah, you could do quite a bit. It might not work out perfectly. And then if you can piece together a lab of just regular computers from someplace, you might be able to run the software that way.
In some schools, what they've done is they've bought these laptops and put them on carts, and if you can plan ahead with your school budget that's being put together right now, actually, if that amount of money can be put in a budget for next year, you can purchase one cart of laptops for a building that can be used for courses like this. And by the way, just so you all know, the software, the Solid Ed software is free to schools. But in addition to that, Siemens will permit each student and teacher to load the software on their personal computers at home at no cost.
Yeah, we'll just make the caveat that it's for educational use only, not for commercial. But yeah, it's
that's correct. All right, here's the next question. Is this a middle school or high school or both? And
Uh,
also, let me start
Go
with
ahead.
this, Tom. The curriculum essentially was designed for grades 9 through 12. However, it can be used in the middle school. You might not use all the projects because those middle students will likely proceed through the curriculum a little bit slower. And there may need to be more teacher-directed instruction in some cases than you might do with older, more mature students. But we do have some middle schools that are using this, and it's a great launch to capture students' interest, particularly in grade 8, so that when they get to high school, where these courses are available, they'll be more likely to pursue those programs in greater numbers.
Yeah, and I was just going to chime in on that same note that like seventh graders would really perform at a different level than juniors would if they were doing this. That doesn't make it good or bad. It offers all kinds of benefits to students of any age. It's just an expectations piece. How about the next question, Dick?
Yeah, well, the next question is related to middle school as well, except in this case, the question is this curriculum, can it be a replacement for 8th grade science or more of an elective course?
Yeah, well, that's, most school districts have like a standards pacing guide for their science. So, this course won't cover all those standards that, they want covered. I think it would be a really great addition to science class because it really gets at those standards that talk about engineering design and how the science is really applied to things. So I think it's well worthwhile doing and trying, but it's not a replacement for an existing science course.
And in addition to that, we have found that science teachers and math teachers really gravitate to curriculum like this because it puts their standards in a context that's being taught through problem-based learning. So that's another aspect of how this can be motivational for science teachers to get involved.
So I just put up a slide with our contact information on in case you want to, shoot us an email or a text or give us a call so we can answer some questions. Do we have more questions, Dick, or did we get to the end?
I think we pretty much got to the end, unless there's some questions that we can think of that have not been asked that we have heard before. One question that I remember is, are these courses sequential and do they fit one grade better than another? And Tom, why don't you answer the sequential part?
Well, they're designed to be sequential. That being said, it doesn't necessarily require a sequential piece. If you have very mature juniors and seniors, they could do some research and come up with the drawing and pieces, or you could almost cherry pick and make a course out of this. I know I heard from a couple of people who wanted it as a capstone to their existing coursework, and they thought that this would make a nice bridge. So they're going to try it without doing the first course, just do the second course as that capstone.
And I think it's very typical to have students across the grades 9 through 12, can be in the same course, same section of the course at the same time. You don't have to isolate students from a particular grade level to be successful.
Well, in a lot of ways, it's better to have a mix of students in the class. It makes more realistic teams, and I think you're going to find that those teams really you know they make the coursework. Just learning how other people think, and that not everybody's the same, and sometimes that's a really good thing. So I would encourage you to try some different things and find out what works in your particular school.
Tom, let me ask you a question. We we hear from people now who are using this curriculum, and if you were to generalize what a teacher would experience starting to teach these classes with their students, what is that experience like, and what is the growth change with teachers as they learn how to use a project problem-based curriculum?
Well, I think you hit the nail on the head where you talk about they get started and then they have to grow into this style of teaching. I talked with a number of people who tried to run the students through all the tutorials and other things at once in the beginning, because they weren't quite comfortable with letting the students explore and experience. And what happens is they don't get that richness of applying what they just learned. And then, the teacher tries to compensate. So if I can get them to slow down and say, okay, we've learned a little chunk and let's apply that chunk and then use that as a basis for the research for the next chunk, the information stays. And then instead of teaching software commands, you're really teaching how to think about design and engineering processes. And it makes for a very rich activity, not only for students, but for the teachers. And I hear from a number of teachers after they get started with things like this that, hey, this is great. They're enjoying it. Teachers tell me they're having a good time and they're no longer the hardest working person in the room. And they seem to think that that's pretty cool too.
Tom, why don't you talk about assessment?
Well, as I mentioned before when we were going through the lesson, there are rubrics. So what I typically used to do is I would keep careful note of their progress in their notebooks, because that is really kind of like their definition of the process that they went through. I was never one on very big on multiple choice tests. I want them to really kind of cement the education in their own minds and do a little metacognition and think about, well, how did they really approach this and what could they have done better?
So Tom, what you're talking about here is formative assessment, right?
Exactly. And as teachers, we do have to have a grade on the report card and things. So I take a look at many of the things in the engineering design notebook. And then I also take a look at things like the writing that I asked them to do in terms of the design brief and maybe a testing protocol and things like that. So did they actually get a chance to do what we asked them to do? And then we'll take a look at their models and how they progress with those. We're not looking for something perfect. What we're looking for is growth.
So Tom, how do you handle the summative assessment at the end of the course?
Well, in this case, it's relatively simple because there is a certification exam that Siemens has, and the students can sit for the certification exam, and it's kind of a good bellwether. It also helps to meet those Perkins requirements that there be an industry certification, tied to the coursework.
What does that cost the schools to do that?
Well, that's something that's provided by Siemens. It actually, students will be able to do that without costs.
So it's free.
Well, nothing's ever free, but without cost to the school district.
Yes, but this Siemens is not charging for anything. They're not charging for the curriculum, they're not charging for the software, and they're not charging for the industry certification exam. Is that correct?
Yeah, that's correct. And Siemens is one of the world's largest corporations, and I think right now they have about 380,000 employees. So they're looking at the next generation of employees, and they deal with companies and governmental organizations in just about every community in the country, and they need talented people in those positions also. So it's in their own best interest to do this and help the schools out to train this next generation.
And just one final point, just to put something on your radar screen, everybody. Tom and I are in discussion with Siemens about developing a third course, and we're working on identifying the right content for that course that would be logical following the first two that we've done. So that's that. And Tom, when's it? Are we doing a webinar in the second course?
Yeah, we're doing a webinar in November on the second course, and there should be an advertisement going out
On the
specifying the
21st?
date and the time.
On the 21st at 1 o'clock, right? Eastern time?
I want to say yes, but I'm not looking at my calendar now, so I'd probably say yes.
Well, I am.
Okay.
Yeah. All right. That's all I can think of.
Well, thanks everybody for coming. We hope you got some good information out of this. And if you have questions, make sure you give us a communication and we'll get back to you.
Goodbye.
Thanks.